Hello. Today we're going to start on chapter 3 of Strogatz chaos theory, which is about bifurcations. So previously we talked about the system x dot is equal to f of x. And if I were to graph some function f of x here, x and x dot, I can determine the behavior of my system x of t, and I interpret it as just flow on this x-axis. Okay. And whenever f of x is positive, I know the flow is going to be to the right. When f of x is negative, the flow is going to be to the left, as follows. And then I know that these intersections at 0 are fixed points, and their stability is determined by whether or not the flow goes into them or diverges away. Sometimes it does one on one side and diverges on the other side, which would be half stable. Now, this is great, but the system, once we've determined all these fixed points, the system is totally locked in here. There's not much more that can be done. We know that the flow on the line is only going to be monotonous in one direction, and it's either going to approach a fixed point or just diverge to infinity. There's no other possible behavior in this dimension 1 system. So the only really interesting thing to do is to start changing the f of x by varying it according to some parameter and then analyzing the effect of the fixed points, okay? And so by changing f of x, we can make fixed points appear or disappear in what are called bifurcations. Okay, so this is what a bifurcation means. And let's talk about the first type of bifurcation, and you'll kind of see what we're talking about. So the first type is a saddle node bifurcation. You're also going to see this a lot. So this bifurcation is characterized by fixed points just being born out of nowhere, okay? And so if I give you x dot is equal to r plus x squared, where r is just a parameter that I'm going to vary, then you'll see that this is the same thing as saying, okay, I have a parabola. Say for r is negative to start out with. I have a parabola. Here's my x dot. Here's my x. And here would be an unstable, and here's a stable fixed point, right? Just by looking at the slopes at the fixed points. And now what I want to look at is as I change r, I'm essentially sliding this parabola up and down. And what's going to happen to these fixed points? Okay. So as I increase r, the parabola is going to shift up until it hits 0 precisely when r equals 0, in fact. When r equals 0, this parabola is going to intersect the x-axis like so, and the fixed points collide and become half stable. So we have a stable and an unstable point colliding, becoming half stable, and then when I further increase r, the fixed points are lost altogether, and the system just goes straight out to positive infinity. And this is the characteristic, almost selfie of a saddle node bifurcation. All right, if you see fixed points colliding and annihilating and then being destroyed, it's almost certainly a saddle node bifurcation, especially in the systems we're going to be looking at. So let's look at another example that's maybe a bit more complex. We have x dot is equal to r minus x minus e to the minus x. Okay, so we want to analyze the effect of varying r here. And we still expect that it's just going to be shifting this graph negative x minus e to the negative x. But that's a little bit confusing to analyze in our minds. Again, we could graph this using a graphing calculator, but we can also use what we know, which is that we know what the graph of r minus x looks like. And we also know what e to the minus x looks like. So if I plot the two together on the same phase plane, okay, I have r minus x here, okay, which has a slope of -1, and then e to the minus x looks something like this. And so by varying r, I'm essentially sliding this blue line vertically up and down, and eventually there's going to be a critical point when it intersects this red line perfectly tangentially. And when that intersection occurs, a fixed point is being born because these two equations, the blue and the red terms here, are going to be equal to each other, and so this thing will go to 0, which is the definition of a fixed point. And then when I slide up the line further, as you can see, I'll draw it maybe over here. As I slide up the line even further, I'm going to have two intersection points, so two fixed points, and one of them is going to be stable. This one should be stable down here, and this one will be unstable up here. Okay, and how I know that is I again look at this equation and I see, okay, r minus x, when the line is above e to the negative x, then x dot is positive, right? Because the blue term dominates, and so I have motion to the right. And then when the blue line dips below e to the minus x, I know that x dot becomes negative, and so my flow is to the left. And so I know that this fixed point is stable, and this fixed point is unstable, okay? All right, and so we can see just by this graphical analysis that this is indeed a saddle node bifurcation because we have this characteristic tangential intersection during which a semi-stable fixed point is born out of nothing and then splits off into a stable and an unstable fixed point. Okay. Another important note is that this intersection always occurs tangentially, and we can use this information to determine a little bit more about our system. So if I require that r minus x equals e to the minus x, okay, so that's the condition for a fixed point, i.e. this is the condition for x dot equals f of x equals 0. And then I also require that f prime of x equals 0, which is essentially the same thing as saying the partial with respect to x of r minus x equals the partial with respect to x of e to the minus x. And notice here, that's corresponding to the fact that we know that these lines are going to have to intersect tangentially. And that's just due to the smooth nature of e to the minus x. Okay, so this tangential intersection in the saddle node bifurcation allows us to set not only the functions equal to each other, but also their derivatives. And so writing this out, we're going to have -1 is equal to negative e to the negative x. And so we can see immediately that x star is equal to 0, which is where the bifurcation is going to occur. And the critical value of r, plugging in x star into the first equation, is just going to be at 1, okay? So this is an important analysis because it's told us exactly the values of r and x star where the system bifurcates. So looking back here, we know that the critical value of r, this bifurcation is going to occur exactly when r is equal to 1, and it's going to occur exactly at x equals 0, okay? All right, so let's move on to the next type of bifurcation. The next type is going to be transcritical. Okay, so transcritical bifurcations are characterized by fixed points being required to stay in the system. So on one hand, we have saddle node bifurcations where the fixed points annihilate and destroy themselves. On the other hand, we have transcritical bifurcations where the fixed points always remain, but they change their stability. So one fixed point gets exchanged stable for unstable with another, okay? And let's kind of look at the normal form for this. So x dot is equal to rx minus x squared. Now, in this case, all right, if I'd graph this picture here, I'm going to have essentially, let's say r is some positive number, this. Okay, and now if I vary r, I'm essentially going to slide this parabola up and down, and this is r. R. Okay, so the next type of bifurcation we're going to talk about is transcritical. Now, this type of bifurcation is characterized by fixed points changing their stability, but their existence still remains. Okay, so the classical example would be x dot is equal to rx minus x squared. And now we're changing the x term instead of the constant term in this parabola as we vary r. So if we factor this out, we have x times r minus x. And we can see that by changing r, we're essentially just sliding the root, which is non-trivial. So we'll have something that looks like this, and then we'll eventually slide over here. So in this first example, here's x dot. And the first black line that I've drawn here, we have r is negative, okay? In which case this non-trivial root is negative, okay? And then this critical case in red occurs when r is equal to 0, in which case there's only one root of multiplicity 2. And then finally, the green case, we have r positive. And if we want to look at this visually on the graphing calculator, I can just show you the process of varying r here. And so you can see that we're sliding the non-trivial root of our parabola. And another interesting observation is that the vertex of the parabola is locked in to the line y equals x squared. So we can also think about just taking this parabola and dragging the vertex along y equals x squared. Now let's do the fixed point analysis for these three different cases. So for the case when r is less than 0, we have, we're going to have an unstable fixed point and a stable fixed point at the origin, okay? And this is, I just am looking at the fact that the slope here at the unstable fixed point is positive, and the slope at the stable fixed point is negative. And then as r increases to 0, these fixed points are again going to collide, okay? So they're again going to collide, r equals 0. And here, motion is entirely to the left, so we have a half stable fixed point. And then, when we continue to increase r, they don't disappear, but rather they just change stability. So now we have, for r greater than 0, all of a sudden the origin becomes unstable, and the non-trivial root becomes stable, okay? And so we can see that this kind of analysis might be super useful in something like population dynamics, where we could have a stable population, and then as some parameters of our environment change, the population could turn unstable and then either drop and decay down to 0, and the species would go extinct. So let's do an example of this transcritical bifurcation. It's a bit more involved. So we have x dot is equal to x times 1 minus x squared minus a is 1 minus e to the negative bx. Okay, and this is an interesting example that Strogatz gives, and he wants us to determine where the bifurcation occurs, and for what values, what range of a and b is this a transcritical bifurcation. Okay. Okay, so we look at this equation and we observe that, first of all, x equals 0 is a fixed point, okay? Because if I plug in x equals 0, this term vanishes, then the exponential goes to 1, and the second term also vanishes to 0, okay? And we observe that this occurs for any value of a and b. So if I term this f of x, then can say f of 0 is equal to 0 for all a and b. And so 0 is always a fixed point of this system. The only way that we can have a bifurcation about the point 0 is if it's a transcritical bifurcation, i.e. We have a change of stability, right? And so let's look for when this might occur. And the way we do this is we're always going to Taylor expand about the fixed point. So this is a crucial kind of method for any analysis of these equations, is if we want to try and garner what type of bifurcation we're observing, we want to try and Taylor expand about a fixed point and then reproduce the normal form for that specific type of bifurcation. Okay, so I'm going to Taylor expand this exponential term here. We have that e to the minus bx is equal to 1 plus negative bx plus b squared x squared over 2 plus higher order terms of x cubed. And the reason why we expand to the second order term in the Taylor expansion is because all of these bifurcations are fundamentally, in the normal form, they're fundamentally parabolic in nature. And so to capture their full behavior, we need to expand the Taylor series out to the second degree term, okay? And it's also due to the fact that a lot of times, for example, in the saddle node bifurcations, we have these tangential intersections. And so the first order Taylor expansion isn't enough because the first two terms are vanishing. So we need to expand to another term and take the second order Taylor expansion, okay? And so plugging this into our equation, we are going to have x minus x cubed, just expanding the first term, minus a times bx minus b squared x squared over 2 plus higher order terms here. All right. And now I'm going to start grouping everything together. So I have, in a little bit, I have 1 minus abx, and then I'm going to have a plus ab squared over 2x squared term. And then this x cubed term, I'm actually just going to group with the higher order terms because it definitely is a higher order term. So I'm just going to add that into my order of x cubed here. All right, this looks great. And now we can kind of see that the normal form is starting to appear, where we have the x term and the normal, and then the transcritical bifurcation will occur when this goes to 0, as we saw earlier. And then we also have our x squared term, and we need to make sure that our x squared term isn't vanishing when the first term does. Okay, so let's just remark. Okay, so ab equals 1. This is when the transcritical bifurcation occurs. And again, I just know this because I know the normal form rx minus x squared, plus or minus, doesn't really matter. I know that this normal form represents a transcritical bifurcation, and that bifurcation occurs precisely when r equals 0. And now the last thing that Strogatz does in this example is he kind of goes a bit further and says that when x is very, very small, so near this near the bifurcation point, when x equals 0, we can neglect this higher order term, and we can realize that near x equals 0, we have that x dot is approximately 1 minus ab x plus ab squared over 2x squared. And then factoring out an x here, I'm going to observe that the non-trivial root is approximately equal to x is equal to negative 1 minus ab times 2 over ab squared, which is basically the fixed point that's non-trivial, right, of our transcritical bifurcation, and I got this equation by just setting this term equal to 0. Okay, so I'm going to do one more example here. This example is also in the book, so let me clear my whiteboard. All right, so we have x dot is equal to r ln of x plus x minus 1. And we want to like analyze this system and look at any bifurcations that might occur, okay? So the first thing I realize is that this system has a clear like fixed point that always exists, okay? By just setting this, this function equal to 0, I observe that x equals 1 is always going to make both of these two terms here immediately go to 0, okay? So x star equals 1 is always a fixed point. So again, if we have a fixed point that's kind of remaining for all of time, we should be suspicious of a transcritical bifurcation, especially if there's a change in stability. So the next step is to Taylor expand around the fixed point, okay? So to do that, I could do it directly, or as Strogatz does, I can do a change of variables. U is equal to x minus 1. And that way I can just do the Taylor expansion about u equals 0, and it will always occur centered at the fixed point. So I observe that u dot is equal to x dot in this case, and this is equal to r ln of u plus 1 plus u, okay? And now I'm going to Taylor expand the natural log term about u equals 0, okay? So natural log of u plus 1 is approximately natural log of 1 plus 1 over 1, and then we have the u term, and then we're going to have a minus u squared over 2, and then plus higher order terms, okay? And you can verify this Taylor expansion on your own. This goes to 0. I'm just going to rewrite this. We have u minus u squared over 2 plus higher order terms. So I'm going to say that u dot is equal to r u minus u squared over 2 plus cubed terms plus u. And now I'm going to group like terms. So we have r plus 1 times u minus r over 2 u squared plus. And I'm just going to bring the r inside of the higher order terms here. Now we have to be a little bit careful, okay? Because notice how I brought the r inside of this higher order term here. And this is only working because the transcritical bifurcation is not occurring at r equals 0, okay? So if we had to worry about r going to 0 in our bifurcation, this would not be as clear because this term would be vanishing, and this term would also be vanishing. So it would be much more complicated. However, we can observe that in this case, our critical value of r is actually going to occur at r critical is -1, because we only care about when the coefficient of the linear term goes to 0 in the transcritical bifurcation. Okay, and so now that I observe that the critical value of r is at -1, and I can see that this is indeed a transcritical, just by looking at the normal form here, I can be certain, since the sign of this u squared term doesn't change as r as r is varied in a neighborhood of -1, but this linear sign is changing. So we are going to have the exact same behavior as in the normal form of the transcritical bifurcation. And we can see this even more clearly if I do a final change of variables to get rid of this r over 2 in the coefficient. So I'm going to set u equal to alpha v, okay? And then I'm going to get that u dot is equal to alpha v dot. And so remember this equation. So I'm plugging this into our equation. We have alpha v dot. And it's important to remember that whenever you do a change of variables, you need to account for that change of variables in the derivative term. You can't only change the variables on the right-hand side of the equation. Okay, so we have r plus 1 alpha v minus r over 2 alpha squared v squared plus, again, higher order in v term now. Okay, and now I'm just going to cancel out the alphas here. So I'm left with v dot is r plus 1 v minus r alpha over 2 v squared plus higher order terms. And now I'm just going to choose my alpha. So I made alpha arbitrary on purpose so that I could just plug it into the equation and see what I should choose for my alpha to get rid of this term. So I'm going to choose 2 over r. And now plugging that in for alpha, I get the exact same equation. V dot is r plus 1 v minus v squared plus higher order terms. And now finally, we can see that we've reconstructed the perfect normal form. And if I wanted to, I could do a final change of variables. R is equal to r plus 1. And then we're just going to get v dot is equal to r v minus v squared plus higher order terms. And there you go. So using these changes of variables, we've essentially reconstructed the normal form for the transcritical bifurcation. And we can indeed show that this occurs when capital R is equal to 0 and at v is equal to 0. And going back to our original variables, which is important, we will observe that we have a little r critical of -1. And then if I go back, I will remember that u was precisely x minus 1. Okay, so we have u is equal to x minus 1, v alpha v is equal to u. So I'm going to get that x is equal to alpha v plus 1. X is equal to 2 over r. 2v over r plus 1. And so our critical point at x is going to occur at x star is equal to 1, as we've already determined because v star is equal to 0. Okay. So this is not super important, this analysis that I just did, except for the fact that we've just changed the variables. Okay, so concluding this example, we've transformed the original differential equation into the normal form, which is boxed above, for the transcritical bifurcation by basically doing a Taylor expansion about the critical point or the fixed point, and then doing a series of changes of variables to kind of reduce the fluff of the equation and just get it to the bare bones normal form. And this is the change of variables that we ended up doing. V is equal to r over 2 times x minus 1, which is, if you just look at that, it's u over alpha. Here's my 1 over alpha, and then here's my u. And then again, we just set capital R equal to little r plus 1 just to get it in the perfect form. And it turns out that for f of x having sufficient smoothness, it's always possible to find an appropriate change of variables to get the equation into the right normal form if you have a specific type of bifurcation. Okay. So just to recap here, the saddle node bifurcation has a normal form x dot is equal to r plus x squared plus or minus. And then the transcritical has a normal form x dot is equal to rx plus or minus x squared. Okay, and then there's one more type of bifurcation that I want to talk about, which is pitchfork bifurcations. But right before we go into pitchfork bifurcations, let me tell you a little bit about bifurcation diagrams. So, let me clear this. So, when we observe bifurcations, it's nice to plot the parameter that we're changing through the bifurcation, and then on the y-axis we want to view the fixed points. Okay, so I want to view the fixed points x star as a function of my changing in parameter. Okay, so if I do this for a saddle node, okay, let's just say the normal form of the saddle node, so r plus x squared is equal to x dot. Observe that when r is greater than 0, we have no fixed points. And for r less than 0, we have fixed points that start to appear and emerge, like so. Okay, now, so the goal of bifurcation diagrams is to represent our system and how it changes directly as a function of changing the parameter r. And specifically, we want to look at how the fixed points of the system change as we change r. Okay, so if we just go back to the saddle node for a minute, we have x dot is equal to r plus x squared. Now let me plot the fixed points x star as a function of a change in parameter r. Okay, so remember, for the saddle node bifurcations, when r is greater than 0, we have no fixed points. So in this region, there's nothing. And then when r hits 0, we have a fixed point is born at x star is equal to 0. And then as r dips down to the negatives, the parabola dips below the x-axis, and we get two fixed points, the left side being stable and the right side being unstable for positive x squared. And so now if we were to graph this on our bifurcation diagram, we would show that as r decreases, we're going to two fixed points are going to be born like so. And then specifically the positive side, so the positive end of the fixed points, is actually going to be unstable. And I'm going to denote this with a dotted line instead of a... Wow, that is gross. Okay. So the dotted line represents the unstable fixed points, and the full black line represents stable fixed points. And so by using these bifurcation diagrams, we can see a lot about the dependence of our system on the parameter r. And now the one thing I can do is that for each fixed value of r, I actually have like an x-axis here, right? So every vertical cross-section actually represents a full x-axis where we have an unstable and a stable fixed point, which is given by this diagram. And so I can directly see the evolution of my system. In this case, I'd plot it along the vertical line. So this is kind of what it might look like. And then in this case, it's a little bit less obvious to tell how the system evolves, but we know that the system is always going to be increasing. So it should go just like this. Okay. So now let's do this for the transcritical bifurcation. So transcritical. Have x dot is equal to rx minus x squared. Now if I plot the fixed points as a function of r, it's going to look a lot different, okay? And I'm going to plot it in red. So essentially, remember that for r less than 0, our diagram is going to look something like this. Okay, here's x dot, here's x. And so we're going to have the non-trivial root is unstable and the origin is stable, okay? So here, for r less than 0, the origin is going to be stable. And then turns out that this non-trivial root is undergoing a linear shift as a function of r, because remember how I factored this out, like so. And so the non-trivial root, which is negative, is unstable here, and it's linearly changing with respect to r. And then once we reach the bifurcation point, which is again the origin at x star equals 0 and r equals 0, okay, all of a sudden the origin becomes unstable, and it looks something like this. The origin becomes unstable and the non-trivial root becomes stable. And so in this diagram, we get something that looks like this, okay, where this is unstable. And so essentially you can see the exact behavior of the transcritical bifurcation is that this origin is changing stability. It's going from stable to unstable on the right-hand side. And then the non-trivial root is again going from unstable to stable. So these bifurcation diagrams are super useful to determine the behavior of a system, and also just to see like what types of bifurcations we might have. So, and then yeah, I'll go ahead and draw some of the arrows to just show how the system might evolve with respect to time here. Okay, so yeah, so this blue line again is just this blue line is just representing the actual system x of t, and we can view this as like the actual flow on the line. Okay. All right, let's move on to pitchfork bifurcations. So pitchfork bifurcations are a lot different from saddle node and transcritical in that we actually have one fixed point basically giving birth to 3, okay? And so the normal form for this is going to be x dot is equal to rx minus x cubed, and this will be a plus or minus, okay? But unlike in the other cases we've observed before, there's a very important distinction between this plus and minus root here, okay? So the minus x cubed, this normal form is called a supercritical pitchfork. And then we also have x dot equals rx plus x cubed, which is called a subcritical pitchfork. My spelling is off today. Sorry about that. All right, and so let's analyze these two cases separately. And the reason why we need to distinguish them is that this x cubed is going to play an important role in the birth of the fixed points, and it's either going to be stabilizing or destabilizing depending on its sign, okay? So if we plot x dot is equal to r x minus x cubed, we're going to have a cubic function that looks like this. And now again, we're going to have 3 fixed points. These outer points are going to be stable and the interior is going to be unstable. And then this x term here is basically going to represent the slope at the origin, because the system behaves basically like rx near the origin. This x cubed disappears. And so we can think about changing r in this system as essentially rotating this red line, okay? And so as r, so this case specifically would be r greater than 0. And then when I rotate the slope of this line, I'm going to change the cubic function to look something like this. And essentially these fixed points here are going to collide into the origin and then collapse in together. So essentially here's r equals 0. And we can see that this is stable. And then, and notice how it's stable even though the slope is 0 at the origin, but it's stable. We can just view this by just looking at the sign of x dot with respect to x and kind of drawing our flowchart direction arrows here. And then once I make r negative, I get a cubic that's still just stable at the origin, okay? And so you might think to yourself, like, what's the difference between r equals 0 and r negative, right? And there's actually a big difference. So the origin is stable at r equals 0, but it's what we call critically like slowed down, in that in this instance, the flow is approaching the origin, and it's going to approach the origin exponentially faster than in this case when the slope at the origin is 0, okay? And this critical slowing down phenomena is characteristic of the fact that a bifurcation is about to occur. And then again, if we were to increase r to r greater than 0, all of a sudden the parabola dips, the cubic function dips below the x-axis, and so we get 3 roots instead of 1 on the real axis, and the origin becomes unstable, and the stable fixed points are born on those non-trivial roots of the cubic function. So if we plot the bifurcation diagram for this, and this is called supercritical pitchfork. Plotting the bifurcation diagram, we have that for r less than 0, we have a single fixed point and is stable at the origin. Okay, and then for r greater than 0, that fixed point splits off into 3, so we get the stable branches on the outside, and then the origin becomes unstable. Okay, so this is what our diagram looks like. Okay, and here's the stable branches and unstable. And so we can see why it's called a pitchfork bifurcation, right? I think that becomes more clear with this diagram. And we can also see the behavior of the system is such that if I started here at this fixed point, right? If let's say I was modeling a population or something, I started this fixed point and then I changed r and increased it, okay? Then eventually I would reach the unstable region, but I would only jump a little bit up to the stable branch here. So it's actually like if I wanted to go back to 0, I could just reverse r back to 0 and I would be okay, right? And so this is what we call like a stable perturbation, in that if we cross the bifurcation point, the actual stable points of our system aren't changing like dramatically in a small neighborhood of the bifurcation, okay? And then if we move to subcritical, it's an extremely unstable transition, okay? So x dot is equal to rx plus x cubed. Now, if I draw out the diagram side by side here, we're going to start out with, let's see, start out with r less than 0. And then as we rotate this origin slope to become positive, we're going to get something like this. And here's Okay, but if we look at the stability of these three cases, it turns out that the stability is the opposite of the supercritical pitchfork. So these stable points on the edge are going to be unstable, and the origin is stable. Okay, and then here we just have an unstable origin. Okay, and we can see this by looking at the slope at the origin or just drawing our direction arrows based on the sign of f of x. Now this is very important. If I draw the bifurcation diagram r with respect to x star here, we're going to have something that looks like this. The origin becomes stable. No, sorry. The origin becomes unstable. So it should look something like this, where essentially we have these unstable branches on the top and bottom, and then the stable origin branch, okay? And then the origin, which is stable, these two unstable branches basically collide together and cause the origin to become unstable. And so if we were modeling a population and we had some stable value here, and then we drifted r past 0 and had a subcritical bifurcation, all of a sudden okay, so pitchfork bifurcations are quite different than the previous two examples, because now our normal form is actually going to be a cubic equation. Okay, so our normal form is going to be the form x dot is equal to rx plus or minus x cubed. Okay, and now we have fundamentally different properties because we're allowing there to be three roots. And so it turns out we're going to have a single fixed point that's going to give birth to three fixed points. Okay. So we actually need to treat these two cases very differently and separately, whether or not the x cubed term is positive or negative, because it's going to play a big effect in the stability of our system. If the x cubed term is positive, you can imagine it's going to make the system much more unstable, whereas if the x cubed term is negative, the system becomes stable. And we'll see that. So for the positive case, we have x dot is equal to rx plus x cubed. This is called subcritical. And we want to think of it as like unstable. If we have a negative sign, then we're going to have x dot is equal to rx minus x cubed, and this is called supercritical, which is more stable. So let's look at the supercritical case first, okay? So I want to emphasize this is what we like to call pitchfork bifurcation. And if I draw out what happens is I change r. Essentially, I'm going to start with r negative, and it's going to look something like this, okay? And then when r hits 0, the slope of my origin is going to be 0. And then for r greater than 0, going to have a positive slope at the origin, like so. So I can think about the effect of changing r as essentially thinking about the tangent line at the origin and just rotating that tangent line. And the slope of that tangent line is precisely r. So when I have a negative slope at the origin, then I'm only going to have the trivial root to my cubic equation here, and it's going to be globally stable, okay? And then when r hits 0, notice how I still have a stable origin, but the trajectories are going to approach the origin a lot slower, okay? And so this is what we call a critical slowing down, when the order of magnitude of how quickly it approaches the origin fundamentally changes. And this is also can be characteristic of a bifurcation that's about to happen if your system has a critical slowing down point. And then finally, when we choose r to be greater than 0, the origin becomes a positive slope, and then we gain two non-trivial roots to our cubic function, and the origin becomes unstable actually. Okay, and so if I were to draw the bifurcation diagram for this system, okay, it's going to look something like this. So we're going to star, no dot, and r. For r less than 0, we have that there's just a stable origin. When r greater than 0, the system bifurcates and we get the two stable branches. Just like this. And then we're going to have an unstable origin. Okay. And so the reason why this is called supercritical or stable is that when we go near the origin, okay, so if we look near the region of the fixed point, the stable nature of the system doesn't change too much. So say we started with a population at 0 and then we changed r to be some small positive number, the stable population is still going to be very small. So we're not going to undergo some huge fluctuation in our population for a very, very small change in r. And this starkly differs in contrast to the subcritical pitchfork, in which case in the neighborhood of your bifurcation, you can have fundamentally different behaviors of your system, and the system can blow up if you increase r the right way. Okay, so let's look at that. All right, so subcritical. So I'm going to have x dot is equal to rx plus x cubed. And now if I plot these things here, so let's plot for r less than 0, r equals to 0, and r greater than 0. Okay, so again, for r less than 0, the slope at our origin is going to be negative, and we have a positive cubic function. So we're going to have something that looks like this. Okay. For r equals 0, we're going to have looks like this, and then for r greater than 0, the slope at our origin is going to become positive, and we're going to get a cubic function like that. And now if I analyze the stability here, at the origin, I start off with a stable origin and unstable branches here. And then these unstable branches essentially collide into the origin and makes the origin unstable. All right. And so let's look at the bifurcation diagram and just kind of plot what happens here. So if I draw my bifurcation diagram, actually I want to make this small. I'm going to have x star and r. For r less than 0, I'm going to have 3 critical points like this, and then the origin will be stable. I'm going to have 3 fixed points, and then at the bifurcation at the origin becomes unstable, and these branches disappear. And so now we can clearly see that in this region, my system can behave very differently. If I started on this stable branch, I could have a stable population size, and then as I underwent this bifurcation, the population could suddenly become unstable and diverge out to infinity. Okay. And the example that he gives in the book for this is if I have like a block that's sitting on a post, and say I just steadily start pouring sand into this block. Okay, so at first the post can fully support the block and everything's fine, right? But then eventually, once I put enough sand in this block and fill it to the very rim, the post can no longer support the block and the system becomes unstable. And then eventually it's going to either break in one direction or the other, and the box will fall down. Okay, so this is kind of an example of a system that could go from a stable to an unstable state, and this can have drastic consequences in fields of science and engineering. All right, so now that we've talked about the supercritical and the subcritical, I want to go over a key example in the book. And he actually leaves the work to the reader for this case. And so I'm going to do the work of the reader and actually analyze this system for you. We have x dot is equal to rx plus x cubed minus x to the fifth. Okay, so this is basically the more realistic pitchfork, subcritical pitchfork bifurcation, because a lot of times in reality, we're not going to have a system that can actually physically go to infinity like this. So really what we want is just some sort of more stable branches on the outside here, that kind of the system that represent just like some extreme values of the system that it bifurcates to during the subcritical bifurcation. So let's analyze this system. Now, the first thing I want to do here is observe that the origin is always a fixed point. And now I'm going to look for other fixed points of the system. Okay, so again, fixed points are just going to be roots of the function f of x. So I'm going to factor out the x term here. I'm going to have r plus x squared minus x to the fourth is equal to 0. And now I'm going to get rid of the x by assuming that, by just saying, okay, we've already identified that 0 is a root. So let's assume that x is non-zero. And then we can get rid of this term here. So I have r plus x squared minus x to the fourth is equal to 0. So I'm going to observe that this is a quadratic function in terms of x squared. So if I do a change of variables, u is equal to x squared, noting that u must be positive, I'm going to have r plus u minus u squared is equal to 0. Okay, and now I can apply the quadratic formula to give me that u star is equal to negative 1 plus or minus the square root of 1 plus 4r divided by 2. And I'm going to bring the 2 inside, and so I'm going to have negative 1/2 plus or minus the square root of 1/4 plus r. Okay. And notice that this is actually x squared. So I'm going to write x star as the square root. So this is x squared. We'll take the square root of this. So we have plus or minus the square root of, I'm sorry, this should be a negative 2 here. So this becomes a plus. This becomes a minus. Okay, so I have okay, so looking at this equation, I see that I have a fixed point at the origin that always exists for all values of r. So I'm going to try to look for non-trivial roots of f of x. So let's factor out an x here. And now if I assume that x is non-zero, and I set f of x equal to 0 to find the fixed points, I can go ahead and cancel out this x term, and I'm left with the equation r plus x squared minus x to the fourth is equal to 0. And we can just see that this is a quadratic equation in x squared. So I'm going to do a change of variables, u is equal to x squared, noting that u has to be strictly positive. X is non-zero. So we have r plus u minus u squared is equal to 0. And now plugging this into the quadratic equation, I have u is equal to plus or minus, negative 1 plus or minus the square root of 1 plus 4r all over negative 2. And now simplifying here, I'm going to have 1/2 plus or minus, and then I'm going to bring this negative just inside the plus or minus. Doesn't matter. We account for that. And then I bring the 2 inside the square root, and so I have a 1/4 plus r. And yeah, essentially I can bring the negative sign into the plus or minus. The plus becomes a minus, the minus becomes a plus, and we still have a plus minus, okay? And now I want to look at when this u is real valued, okay? So u is real when r is greater than negative 1/4, okay? And just by looking at the inside of this square root here. And then also, since remember that we have this condition that u has to be strictly positive, okay? We also want to check for when u is positive. So u is positive. Well, it's always positive when I take the positive conjugate, okay? So always for positive conjugate. And then for the negative conjugate, it's when 1/2 is greater than square root of 1/4 plus r. This is for the negative conjugate. And doing the algebra here, we realize that this expression is precisely equal to r less than 0, okay? So essentially, we're going to have that, summarizing this analysis, we have when r is less than negative 1/4, we are only going to have one root, so u is complex. Thus, the only fixed point is just at 0. When r is between minus 1/4 and 0, all of a sudden u becomes real. And in fact, u is positive for the positive conjugate and for the negative conjugate, okay? Because r is still negative. And so we're actually going to have two values of u. So u is equal to 1/2 plus or minus the square root of 1/4 plus r. And remember, this is x squared. So this is going to end up being 4 non-trivial roots. And so we actually get 5 roots, including the trivial root at the origin. So we get x star is equal to plus or minus the square root of 1/2 plus or minus square root of 1/4 plus r. And then finally, when r becomes greater than 0, we can see that u is still real, but u is negative when we take the negative conjugate here. And so we only have that u is equal to 1/2 plus the square root of 1/4 plus r. And so our roots are x star is equal to plus or minus the square root of just 1/2 plus the square root of 1/4 plus r. And I should add here that x star equals 0 is still a root in both of these cases. Okay, so graphically, we have one fixed point here, 5 fixed points in this case, and then 3 fixed points in the case where r is greater than 0. Whenever the number of fixed points changes, we can be pretty certain that a bifurcation is happening, because something about the behavior of our system is changing and fixed points are either being born or destroyed, okay? And so it's really interesting that here we go from 1 directly to 5, and then we go to 3 fixed points. So let's try to draw a bifurcation diagram and see what this might look like graphically. Okay, so if I look at r as a x star as a function of r, I'm going to have these two critical values of negative 1/4 and 0 for my r values. And then, so I'm going to have, and actually I'm not going to talk about stability yet. We'll do the stability analysis in a moment. But we'll always have a fixed point along this origin here. So I'll just draw a line here along the origin. A bit bigger. Okay. And then at negative 1/4, we're actually going to get 2 saddle node bifurcations, okay? And so fixed points are going to be born out of thin air. And then these outer fixed points, okay, corresponding to the positive conjugate here of the x star, these ones will always exist as long as this expression is well defined. So for r greater than negative 1/4. However, when r becomes positive, all of a sudden these inner fixed points, okay, so the ones corresponding to this negative conjugate disappear and become complex. So we're going to have something that looks like this. And then these are going to disappear. And so as we can see, we can expect some sort of pitchfork at the origin and some sort of saddle node at r equals negative 1/4. Okay, so let's do the analysis here. Okay, so what I'm going to do is I'm going to do a stability analysis by plugging in values for f prime of x. All right. So first of all, f of x is rx plus x cubed minus x to the fifth. So f prime of x is just r plus 3x squared minus 5x to the fourth. And then our x star value was plus or minus square root of 1/2 plus or minus square root of 1 plus 1/4 plus r. Okay, so I'm just going to go ahead and plug this into f prime and try to determine if f prime is positive or negative. So plugging this value in, I'm going to get r plus 3 times 1/2 plus or minus the square root of r plus 1/4 minus 5 times 1/2 plus or minus square root of r plus 1/4 squared. Now I'm going to expand this term. So I'm going to get so we're just going to have 1/4, and then because it's a perfect square, the plus or minus will be preserved, and the 1/2 will add to be 1, and we'll just have a plus r plus 1/4 here. And then we're going to square the final term, so we'll just get a plus r plus 1/4 here. Okay. And now I'm going to start combining like terms. So I'm going to observe that I have 3/2 here, 5/4 here. So this is going to give me an r plus 1/4. And then here I have a 3 plus or minus root r plus 1/4, and I have a negative 5 plus or minus the same. And so I'm going to be left with a minus plus 2 square root of r plus 1/4. And then finally we have a minus 5 r plus 1/4. So combining these terms, these r plus 1/4 terms here, we're just left with f prime at x star is precisely minus 4 r plus 1/4 minus or plus 2 root r plus 1/4. Okay. All right. And now, so observe that first of all, when I have, let's look at the region. Let's look at the region when r is between negative 1/4 and 0. All right. And we'll observe that if I factor out square root of r plus 1/4 here, so I'll factor out a negative 2 square root of r plus 1/4, and then we'll have a 2 root r plus 1/4 plus or minus 1. Okay, so when r is in this interval, if I take the positive conjugate here, I'm going to have a stable fixed point. So positive is going to make this whole term negative. Whereas if I take the negative conjugate, notice that this term here is actually going to be less than 1. And so therefore taking the negative conjugate will give me a negative number, and in fact give me a positive final answer, canceling with this negative here. So if I take the negative conjugate, I get the f prime is positive. Okay, so the positive, remember that the positive conjugate corresponds, if we go back to our diagram here. Wow, my computer's freezing up. Sorry about that. Okay, so let's move back to our diagram. So remember that the positive conjugate corresponded to this outer branch, okay? And we just determined, we did an analysis, we determined that this outer branch is going to be stable because the derivative, when we plug in the fixed point, is going to be negative. And similarly here, this is also corresponding to the positive conjugate, okay? And then the negative conjugate, we just determined is actually going to be unstable, okay? Let's go back just so you can see it. Yeah, so the negative conjugate is this inner branch, and it's going to cause the derivative to be positive in the region between negative 1/4 and 0. And so that's going to correspond, positive derivative corresponds to an unstable fixed point, okay? So this fixed point is going to be unstable here. And now finally, let's do the analysis of the origin, okay? So this one's actually a lot easier to do, thankfully. We look at f prime of x. Let's find it. So we just look at f prime of x and we plug in x equals 0 here, and we just get r. So f prime of 0 is equal to r. And therefore, we have for r greater than 0, the origin is unstable. And when r is less than 0, the origin is stable. Okay. So going back to our diagram, we have that r less than 0 is stable as shown here, and then r greater than 0 is going to be unstable. Okay, and then I want to just kind of erase these lines to just make it even more clear. So here we're going to have unstable. Okay, and so this is the bifurcation diagram for our system, and this tells us a lot. So first of all, it tells us that we have two saddle node bifurcations that are occurring at r critical is negative 1/4. Okay, and then we're going to have a subcritical pitchfork bifurcation at the origin when r is equal to 0, okay? And the value of r, the value of x star at these saddle node bifurcations can simply be determined by plugging in the respective value for r into f of x and then solving for the roots of the equation, okay? And so, I hope this was helpful. And the system is basically what scientists might use instead of a classical subcritical pitchfork, because we still have the hysteresis feature. Okay, and you might be wondering, like, how did I graph this? How did I graph these parabolas here? How did I know that they started and they looked like a saddle node to begin with? So it turns out that the graphs of these curves are actually just given by the formulas we calculated for x star. So we have plus or minus the square root of 1/2 plus or minus the square root of 1/4 plus r. Okay, and so essentially these curves are precisely given. So these curves in blue are precisely given by the plus and minus of the positive conjugate. And then these curves, these unstable curves in green here, are precisely given also by the plus and minus, but the negative conjugate of the inside square root, okay? And so all of the analysis that we did algebraically to determine the roots of the equation and also to determine their stability can then immediately be used to plot the bifurcation diagram, which is entirely just the fixed points as a function of r. And so if we go to Desmos, I have this for you. here, you can see that I went ahead and I can show you exactly what this looks like graphically when I plug in all of the different conjugates of these roots. And I kind of added the dotted lines just for emphasis on stability here. But yeah, exactly what we expected. At 1/4, we have these saddle node bifurcations, and then at 0 we have a subcritical pitchfork. Now, one last thing I'll show you on this model here is that if we just look at our original f of x, okay, and we vary r. So say we start r at some very negative value, okay? So as we start to vary r, we'll see what happens to the curve f of x. So at our first bifurcation point, we can see that these parabolic pieces of this curve begin to intersect the x-axis tangentially. Okay, and that's our saddle node bifurcation, and we go from having one root to having 5. And then as r continues to increase and becomes positive, then these interior roots, you can see here and here, they just collide with the origin and cause the origin to become unstable. Okay, but these outer branches are always going to remain stable. And so what I'll mention is that the relevance of this in science is that we might have a system that undergoes what Strogatz calls hysteresis, okay? Where, say we start our system, let's draw our diagram again. So we have stable, unstable here. Okay, so if we started out like at this stable value here, and then we start pushing out r. So remember that I can always draw a vertical cross section and analyze the actual flow of my system on this cross section here. So like so. And so if my population was at the origin at some stable value, and then I start increasing r, and I reach this critical point here, and then I bifurcate. All of a sudden, my system, if it's perturbed by some slight amount, is going to, if it's out here, it's going to immediately drop down onto this stable branch that's much further away, so at some extremely high value, right? So the system's going to go under this radical shift in the neighborhood of the origin. And then let's say that I didn't want this to happen. Let's say I wanted my system to remain on the origin. If I tried to reverse it back and I tried to decrease r to fix my system, I'd have to keep decreasing r, and the system would have to move along this stable branch until I finally go past -1/4, until which case it could finally return back to the origin. So it's an irreversible change that occurs in the system. In order to fully return to the initial state, you'd have to push r much further back once you've already jumped away to the stable branches on the edge. Okay, and so this is a phenomenon known as hysteresis, and it's essentially when we have a change in our system that's not immediately reversible. Okay, and if I could find his definition is a lack of reversibility as a parameter is varied. Okay. Yeah, I think this is a great coverage of chapter 3. There's a few more complicated examples where we go into like two different parameters. Say I introduce like a and b instead of just one r, and we kind of look at the effects of that. And I'll cover that section of the chapter in later videos when we kind of go more into the exercises. I think this is all the crucial concepts that you need to know about bifurcations for right now. So, all right, have a nice day.